Today we're going to continue to look at the triangle sum theorem. If you'll remember way back in topic 2, we started looking at the sum of the angles of triangles, and we reviewed something that you should have possibly learned in 7th grade when you started looking at the angles of a triangle. And that was the way that you could prove that they always add up to be 180 degrees. So that activity would take a triangle and just tear off the 3 angles of the triangle, as you can see here, and then rearrange those so that those vertices all are connecting at one single point. So we'd have to turn the B around and the A around and the C around so that the vertices of all 3 angles are at this one point. By doing that, we can see that all 3 of these angles make a straight angle together. And since we know a straight angle is 180 degrees, then we know that these 3 angles add up to be 180 degrees. So what we're going to look at today is there another way that we could prove this conjecture? Remember, once we prove our conjectures, they become theorems, and this is known as the triangle sum theorem. So since I'm not with you today, you're not going to actually get to do the patty paper activity yourselves. I know that makes some of you very, very sad, but I'm going to show you the patty paper activity we would have done together if I would have been there with you. So I just have a regular triangle here that I've labeled the vertices as A, B, and C. And I'm not bleeding, by the way, if you see this red on my hands. My red pen exploded on me. I'm sure it had something to do with the dogs biting on it, but don't be afraid that I'm bleeding. So I have a regular triangle ABC. It's not special in any way. It's not an equilateral triangle, isosceles, right, anything like that. It's just a regular old triangle. And so the first fold that's required in this patty paper exercise is a little difficult, so I know you're even more sad now that you're not doing this yourself. But you have to make the altitude from vertex B. And remember, an altitude starts at a vertex and is perpendicular to the opposite side. So that fold was even a little difficult for me, but I've got it pre-folded now, so you don't have to watch me struggle with that. But it's got to go through point B, and I've got these, the edge here, all going collinear so that I know that that's a right angle that's created with that fold. And I'm labeling that intersection down here as point D, and I've got a little box here just to remind me that's a right angle. And so at that point, the fold that we do next is to fold point B on top of point D. And so I've already done that fold here, and you can see B and D are the same point when I make that fold. That creates these 2 points that I've labeled as E and F. And then the third and fourth fold, if we keep this folded down with B, is to fold A to that point D and to fold C to that point D. So it kind of reminds me of an envelope once you have it all folded all together like this. And so now we're going to use this paper folding to answer some of the questions in your notes. So we're going to look at answers to 1 through 4 on your notes using our patty paper here. So the first question is, in the triangle ABC, what is the sum of the measures of angle A, B, and C? So we can see by this paper folding that by folding it this way, we have the same effect as the previous activity, where we have angles A, B, and C together making a straight angle. So that just shows us again that the 3 would have to add up to be 180 degrees. Anytime you're asked to explain why this is true, make sure that you do so mathematically, and it's because the 3 angles form a straight angle together. So the definition of a straight angle is an angle that has a measure of 180 degrees. One angle with 180 degrees. So number 2 says, in triangle ABC, what is true about the measures of angles A and C if angle B is a right angle? So if this angle had been a right angle, we know that means it's 90 degrees. So if they all 3 have to add up to be 180, and one of them is 90, that means the other 2 make up the rest of the 180 degrees, which is another 90 degrees that are left. So we're taking away 90 degrees from 180. There's 90 degrees left for these 2 angles. So the measure of angle A and the measure of angle C together would have to add to be 90 degrees. Now we have a special name for that. Anytime we have two angles adding to be 90 degrees, we call those complementary angles. Remember, it's with an E here, not an I. They're not being nice to one another. They complement each other in the way that they make each other add to be 90 degrees. Okay, questions 3 and 4 go back to our folding here. And so it says, how does segment EF relate to segment AC? So I'm going to look at that with some measurements here with my ruler. So I'm going to measure segment EF and segment AC. And I'm going to do so with centimeters just to make it a little bit easier on me. So if I don't know if you can see that very clearly on the ladybug, but you'll just have to trust me if you can't read it, that E to F is exactly 6 centimeters long. Well, if I measure A to C down here, I will see that it, again, you may not be able to see, but it is exactly 12 centimeters long. And so the relationship along the lengths, if this one's 6 and this one's 12, is that the length of EF is half of the length of AC. Now remember, when I'm talking about their lengths, I don't put segment bars above the 2 points. I don't use them, and I'm showing that that means it's a number I'm talking about. So the measurement from E to F is half of the measurement from A to C. And remember, E to F in my drawing was 6 centimeters, and A to C was 12 centimeters. So then also on number 4, it wants to know how points E and F relate to the segments that they're on. So E is on the segment AB, and F is on the segment BC. So again, I'm going to measure to show you this relationship here. And so if I look at A to E, it's not exactly at 5 centimeters, it's about 52 millimeters. If I measure E to B, also at 52 millimeters. So if A to E and E to B are both 52 millimeters, then we know that their lengths are equal to each other. And on my drawing, they were 52 millimeters apiece. Let's look at the relationship between BF and FC. So I can measure from B to F, and it looks like we're exactly at 6 centimeters. F to C is also exactly 6 centimeters. So we find that B to F and F to C are also equal in measure. They were exactly 6 centimeters. Now there's nothing special about that being the same as EF. That just was something that happened with my special triangle here. It's not something that is a relationship we see all the time. But this is something that we see with this type of folding here. So if E is separating AB into 2 congruent parts, I can put a tick mark on each of those parts to show they're congruent. And F is separating B to C into 2 congruent parts. Now when I put tick marks there, I don't want to put 1 again, because that would say that E to B and B to F are the same length, and they're not. They're not the same. So I'm using 2 tick marks over here to show they're congruent to each other, but not to these measurements on the other side. So we know what these points are called. E and F have a special name. So E and F are both midpoints of the sides that they're on, since they're separating that segment into congruent parts. So E is the midpoint of segment AB, and F is the midpoint of segment BC. Okay, I'm going to stop the video and start another one here.